Hello everyone, welcome to my second forum talk this week. My name is Jac van Egmond, and today I'll be talking all about understanding aerodynamics through a new lens, and that lens is CFD, or Computational Fluid Dynamics. And what you see here is actually a great example of that. I'm sure you'll all recognize the airfoil, but it's probably in a color scheme that you've never seen before. And it's actually a very insightful image, and I hope today you'll leave feeling the same. Now, I think a good starting point is to tell you a little bit more about myself. I really got into aerodynamics when I was studying at Delft University. And in 2010, I joined a team with the task of designing and building the world's most fuel-efficient car. And you can see me holding up the carbon body here. It weighed around 9 pounds, and the whole car ended up weighing around 88 pounds. Now, I was responsible for the aerodynamic design of this car, and at 20 miles per hour, we have a drag force of less than a quarter pound. Now, I believe it was around 2% of a horsepower to power this car. And if you relate that to pure fuel efficiency, you're getting in the range of 6,000 to 7,000 miles to the gallon. So you can save quite a bit if you lose all comfort. Now, while designing this car, I used a panel code called VS Aero. It was pretty good, a very good program. As you can see in the top, we have a surface velocity, and on the bottom you can see some streamlines. But when I was working on this design, I always wanted to see a little bit more. I always wanted to understand what the airflow was doing at a higher level of detail. So a couple of years later, I graduated, and I could start my own company, MV Aero. And I wanted to do nothing more than use high-fidelity CFD every day to better understand aerodynamics. And finally, I was able to see what was really going on. Now, that really never changed over the next 10 years or so. I've worked with CFD pretty much every day. I've met a lot of interesting people all over the world, and my goal is really to work on the most interesting projects around the world. And over these years, I've gained a lot of insights from doing the CFD work, and I'm going to try today to share some of these insights with you. Now, we're going to go over a couple of topics, and we're going to go over them not really in a mathematical way, but rather in a very conceptual way. I'm going to try and bring across as much conceptual understanding as I can within the time limit of 1 hour. So let's start at the very fundamental aerodynamic lift. Now, here's a wing section, and whenever the wing is moving from right to left, we can ask ourselves the fundamental question: what is this wing actually doing to the air? Well, over a certain time step, this wing is moving forward. So it's actually in a new position after a certain time step. As you can see, in blue would be the new position, and in gray we have the old position. Now, part of the volume of the new and old position overlap, and here nothing really interesting happens. A wing was occupying the space before, and a wing is occupying the space now. But the interesting thing happens at both the front and the rear of the wing, because the rear of the front of the wing now occupies a new space, so therefore it must have pushed air out. While at the back it has now evacuated space and must have left space behind. Well, that's space where new air can come rushing in. So we can say see, for that type of aircraft, we would need a really small time step. But we can see that the front of the wing is compressing the air, pushing it away while the back of the wing is evacuating space for new air to rush into. So really, already, very fundamentally, we have this natural tendency of a high pressure at the front that needs to find a new home. And eventually, one way or another, you can think of it as it will find its home at the back. This is creating an equal amount of volume in the back. Now, when we start to look at that in CFD, we find exactly what we should find. And this is a simulation of a symmetrical section at 0 degrees angles of attack. And we run the simulation and we hit pause after a very short time interval. Now, we see in red a very high pressure at the front, and in blue we see negative pressure at the back. Now the current situation is very imbalanced. It's definitely not in a steady state. And in general, we can think of this high pressure zone wanting to go to the low pressure zone. If we look at that in CFD now, notice the waves propagating outward. This is the speed of sound. And as time moves on, the pressures equalize in the only way that they can. And the high pressures, areas of high pressures resolve to areas of low pressure. And this is probably a pressure distribution that most of you are more familiar with. This is the steady state result. Now if we look at that in 2D and just plot so what we've just seen, we're now plotting in 2D, and we're looking at a surface pressure gradient over that exact airfoil. As we can tell here is we have stagnation pressure at the leading edge, and then from there on air speeds up all the way to the apex of the pressure distribution, after which it will encounter more and more pressure until it slows down. Now we can look at the exact same simulation we've just seen, but now we're going to look at a velocity profile, a velocity color contour. And as we can see, we indeed slow down with the little blue dot, that's the stagnation point, and accelerate then over the airfoil. Now that's an airfoil with 0 angle of attack and a symmetrical section, and things get a lot more interesting once we start to introduce angle of attack. Again, we look at this very simple but fundamental picture. What is this wing actually doing while going through the air? Well, it's creating compression at the front and evacuation at the back. And this compression at the front, as you can see at an angle of attack, has now moved also towards the bottom of the surface, while the evacuation zone has now also moved to the top surface. So we already notice an asymmetry here. And we find exactly that in CFD whenever we run a simulation and hit pause after a very short time interval. We notice very high pressures at the leading edge and at the bottom in general, while we have negative pressure up top. Now when we're trying to resolve that, the flow will start to get into equilibrium over time, and it's doing that in the only way it can. It's moving the high pressure zone to the low pressure zone over the top surface of the airfoil. This in the end creates a steady state pressure distribution that looks pretty familiar to most of you. With very high speeds, in blue is pressure now, but those are very high local velocities. If we then plot exactly what we just saw, but we're just going to plot it on the surface of the airfoil, we immediately notice now an asymmetry in the pressure distribution on the top and bottom surface. That means we're now generating lift. In flow, as you can see, the pressure peak is pretty high, negative pressure peak. The flow is moving quite fast. And we see that in the simulation also. Because of an increased angle of attack, we are also now implementing a new phenomenon. it's the trailing vortex. We are now lifting, we're now generating a force, and to have that force we need to push down on something. We're pushing down on the air. Notice the slight angle, that's called the downwash angle. So we need to push something down in order to lift. Lift comes at a cost, it's never free. We need to actually give kinetic energy to the air in order to move down. That's the only way we can get lift. And we will feel that energy requirement as drag. That's why it's called lift-induced drag. So we're definitely creating a force which we call lift. And we know that all forces need to obey Newton's law, force is mass times acceleration. And this law is pretty obvious for most rigid bodies. We usually know what the mass of that body is, we usually know what the force is, and we can very accurately say what the acceleration is going to be. But things are a little different for air. We could ask, whenever we're lifting, what exactly is the mass that we're pushing down? And then a follow-up question would be, what exactly is the acceleration that we're giving to that air? Well, the mass really has to do, it can only be the air, and it can only be the air that is affected by the wing. It's sort of the column of air, as you can see there, that the wing is affecting. And then hence the acceleration then is the downward velocity given to that mass. For a given lift force then, we can think of two situations and basically anything in between. On the left you see a situation that's very similar to most wind tunnel setups. We have a limited height, a limited column of air that can be affected by the wing, and therefore for a certain lift force, our acceleration needs to be quite high. On the right is more closely akin to an open air situation, and we have a lot of mass that we can potentially reach with our wing, and we'll have a low acceleration for a given amount of lift. Now, our atmosphere is about 62 miles high, so a wing section in theory can affect a lot of mass. And if we have a wing section that can actually affect the entire atmosphere all the way up to 62 miles, all the way down to ground level, then our acceleration is always going to be negligible. It's always going to be so small, even at very high lift. And that's why they say usually a 2D section does not cause any induced drag, or an infinite span does not cause any induced drag. But this is only true if our atmosphere is really infinite. But it's fundamentally really not true with a limited atmosphere. And that brings us to three-dimensional effects. You might have seen a picture like this. This is the downwash of a wing, and you can notice the vortex roll up in the wake. Things get a little bit more complicated in 3D. We still have our lift force, and our lift force is usually not the most complicated thing to figure out. But we can ask again, what's going to be our mass and what's going to be our acceleration? Well, if we look at a wing from the most basic idea possible, it's simply a geometric plane that is trying to separate high pressure from low pressure. And that already tells us a lot, because at the tips of the wing it cannot sustain this pressure difference. So it cannot produce any force. And if it cannot produce any force, that means it's not affecting any mass, it's not accelerating any air down. But a little further inboard, we can ask ourselves the question, how much air, what is the height of column of air that this section of the wing will affect? Will we say maybe 10 feet, maybe 100 feet, maybe even the entirety of the atmosphere, 62 miles? Well, as it turns out, the following is both a very accurate and also a very insightful approximation. We do have zero mass affected by the wing at the tips, as you can see. but the column of air that we affect by our center section, that our center section is able to affect, is equal in height as our span. And that then makes that the whole distribution, if we look at the column of air for each section of the span, becomes distributed like this, like a circle. Now, that's pretty interesting because that means the longer we have our wingspan, the more air the wing will affect. If we double our span, our wing will affect quadruple the amount of air. That's huge. And it's pretty interesting to do a little pop quiz. And we're going to look at 3 different wings. We have wing A, it's 20 feet in span, it's lifting 1,000 pounds. We have wing B, double the span, lifting double the weight, 2,000 pounds. And then we have wing C, 80 feet span, and doubling the weight again to 4,000 pounds. Now all 3 wings are flying by themselves at 100 knots at 3,000 feet altitude. And we can ask ourselves this question, which wing will exhibit the most induced drag? So I'll give you all a couple seconds to think about this. Anyone dare to give a, yeah?
I think you're all the same.
Well, this guy's been paying attention. It's not exactly a trick question like yesterday, but it's a very good answer. The drag on each wing is going to be exactly the same. It's going to be around 30 pounds of induced drag. So that tells you a lot about how span can affect drag. It's pretty incredible, really. We double the wingspan, we double our lifting capability, but our induced drag does not go up at all. So our L over D in terms of lift compared to induced drag is rising very quickly with increase in span. And that really all comes back to this fundamental idea of force is mass times acceleration. We want the acceleration to be as low as possible. That's the kinetic energy that we're giving to the air. Well, the larger the span, the more air mass we can affect, and therefore the lower the acceleration. The same is true for the other 2. If we want to reduce induced drag, we simply fly at a lower altitude. And the mass will be higher because the density will be higher. Or we can fly faster. That's another option, because we will encounter more air mass over a given period of time. And all 3 are very valid avenues to reduce induced drag. But there is one more option that we can take to decrease induced drag. We can use winglets to make it a little more difficult for the air to equalize pressure at the tip. So here you see 2 wings with identical lift, identical span, identical density, and identical airspeed. Notice the relatively strong wingtip vortex for the wing on the bottom compared to the wing on top, where we have rather 2 split vortices. So we have 2 weaker vortices rather than a single strong one. Now, what is this winglet doing fundamentally? If we again look at the front view of a wing, the winglet is basically trying to prevent that no lift condition, that zero lift condition at the tip by not allowing the pressure to release immediately. Now, that doesn't just have an effect locally. It's not just that the winglet is affecting the wingtip vortex locally, rather it is improving the situation for the entire wing. We are no longer have a circular mass distribution that we affect. In fact, the column of air that the center section affect is increasing as well. So the overall span efficiency for the wing is increasing. Now, if you take one thing away from the presentation so far, I think it should be that induced drag is simply the kinetic energy investment that we need to give it in order to generate lift, in order to push it down. And I think if you truly grasp that, if you take this as a fundament for your thinking, then you don't really need to rely on the equations. Rather, you can use this idea to use and take a piece of paper and a pen, and you can come up with the equations for induced drag pretty easily yourself. It's not that difficult. Well, that's induced drag. Let's now talk about the other component of drag called parasitic drag. As our wing moves through the air, there's a difference between the velocity of the air and the wing. And that difference in velocity will result in friction. And that will result in a thin layer of air which lost a little bit of kinetic energy due to friction. And we call that layer of air, precisely the layer of air that has lost some energy to friction, we call that the boundary layer. And there are basically three stages that we can identify. We have usually up front a laminar boundary layer associated with relatively low drag. Then we're getting a turbulent boundary layer which is associated with a little bit more drag. And finally we have separation. So we have a little of upstream flow sometimes, and it's associated with relatively high pressure drag. It's a little more fun to look at the same situation in CFD, and now we can actually see the boundary layer evolve in real time. And this will also give you a good sense of the size of the boundary layer relative to the wing. As you can see, the boundary layer transitions around at 60%. And it's pretty interesting to go into a little bit of detail here. So we're just zoomed in. And as you can see, the boundary layer started off thin everywhere. It's only as time moves on that this boundary layer starts to pile up. All the friction that was created at the front of the wing starts to pile up towards the back. The boundary layer then becomes too thick, starts to oscillate, and finally breaks down in a fully turbulent boundary layer. Now that's the transition from a side view. It's also pretty interesting to look at it from a top view. So this is a laminar to turbulent transition. And as you can see, it's happening over several stages. We're looking at a top view. Flow is coming from the left. We're starting with stable laminar flow. And the first thing we notice is we have two-dimensional waves. And these start to change in shape a little bit, where it says spanwise vorticity, and that allows for air, new fresh air to rush in while some of the boundary layer starts to move up. And that's really the first stage towards a full three-dimensional breakdown of the boundary layer. Now, it's a little bit more fun to look at it in CFD. We can look at the transition in 3D, and we notice the spanwise oscillation in the bottom left, and as they progress, they start to change their shape, which indeed allows fresh air to come in towards the surface and older air to move up, almost like these horseshoe vortices, and eventually we have a fully turbulent boundary layer. Now that's really about skin friction, but the other component of parasitic drag would be pressure drag. And pressure drag is simply the difference between the pressure on the front and the back of the geometry. And it's pretty interesting to note, even though the cylinder obviously is going to do a lot worse than the airfoil, because we have skin friction involved, even on the airfoil, it will always exhibit a little bit of pressure drag. Now, I cannot really think of a better way to show you pressure drag than to compare the flow to the tiny red dot that's a cylinder on top versus an airfoil 50 times the chord length. Now, as you can see, the flow coming from the cylinder is very violent. It only affects a small amount of air, but it really affects it by a lot. That is pressure drag. That's a high part of that is pressure drag. In contrast, the airfoil below obviously has a lot more effect on a lot more air, and it also obviously has a lot more skin friction. It's a lot bigger. But its pressure drag is so low, relatively speaking, that these geometries are equal in drag. Now, if we start to simulate at the highest detail, we can really capture all of the effects that we just discussed. We have laminar to turbulent transition, notice the oscillation waves, we have pressure drag coming from the side view mirrors, and we even have full separation at the back of the car. Also notice that the boundary layer, the turbulent boundary layer, is moving significantly slower than the free stream. Now, I think the important takeaway from parasitic drag is that it's simply a wasteful kinetic energy that we give to the air with our airframe. And I say it's wasteful because we're not getting anything back from it. We're not getting any lift from it, like lift-induced drag. Well, so far we've covered aerodynamic lift, induced drag, and parasitic drag. And we need to understand all three of them to design a prop. When we think about a propeller, we can think about what is it that we actually want from the propeller. Well, we wanted to create thrust. We wanted to create a force forwards. And we know, again, that force is mass times acceleration. So we need to push something back in an equivalent way. And again, we can ask, what's our mass and what's our acceleration? Well, to answer those, we resort to momentum theory. And you can see a nice picture of it here. We start with an inflow velocity, very uniform, it could be our flight velocity. And then in the center we have a propulsion system. Some air is going through the propulsion system and it will have an increased velocity. So we're basically pushing air back. Now the mass is always going to be the air that is going through the propulsion system, while the acceleration is the delta in velocity, that's our increase in velocity. And we can look at this in CFD too, it's pretty fun. We create a pressure disk, and as you can see, as time moves on, it provides a perfectly uniform downwash. Not only is the pressure perfectly uniform, but also the increase in velocity is perfectly uniform over the disk. Well, unfortunately, we have yet to invent the pressure disk, and we are currently limited to using rotating blades or propellers. And if we start to look at propellers, let's look at a blade element. Let's look at only a section of a propeller and think about what it should do ideally, what we ideally want it to do. Well, we want a little section on the propeller to create lift in the direction where we want thrust. And conversely, that means that we want the downwash to go straight back. But unfortunately, we hit upon a reality. We are dealing with a single rotating blade, and we not only have the airspeed coming in, but we also have a rotational speed that varies along the blade. As you can see here, that gives us two different velocity triangles, inboard and outboard of the prop. Now, to generate any lift on this airfoil section then, we need to pitch it at some angle, otherwise it won't give us any lift in the direction we want. And then we get a picture like this, where we are generating lift, but it's not completely in line with the direction of thrust that we want. And thereby we also create another vector, another force in the opposite direction of this movement of this section, and that is felt as torque. In a very symmetrical way, our downwash is not going to be aligned with the actual flow in the sense that we want, but it's also having another component that's going to rotate the flow, or called swirl. And this is what you feel whenever you're taking off. You'll feel that on your vertical tail. Well, if we position and size the airfoils perfectly, we can then create a propeller with minimum induced loss that gives us maximum thrust for a given amount of torque. And if we put everything together then, this is what minimum induced loss looks like. Notice that every time the blade cuts through the cross-section, flow is accelerated down. And also notice that after a while, it starts to resemble the pressure disc pretty well. It's not exactly the same, but it comes quite close as you can be, really. Because that gives us the most efficient propeller for any diameter. And that's great. Sometimes the project ends right there. But for some other projects, there could be other considerations as well. And one of them could be noise. Well, if we start to look into noise, we can see empirically from experiment that it is very strongly correlated with tip speed. Or rather, to be a bit more precise, it's very strongly correlated with tip speed expressed in terms of the speed of sound. And whenever we look at a CFD result of a rotating propeller, we can kind of grasp that relationship conceptually. Because not only is the blade tip creating a tip vortex, not unlike a wing, but remember that the blade tip is also moving very fast. So this pressure release at the tip that causes that vortex is happening at very high transonic speeds. And it's precisely the combination of these two that is responsible for a very high noise signature. And that brings us to an interesting question. Well, let's revisit an image we saw earlier. We noticed that the winglet is able to split a strong vortex into two weaker vortices. And we can ask ourselves the question, will that apply to a propeller? Well, I've been working together with Craig Cato for the past 8 years, and this is only a project we've been doing recently, where we're calling it the non-planar propeller because you notice the tips are bent out of plane. It's not quite as radical as a winglet, but it is definitely out of plane. And when we start to look at the tip vortex generation in CFD, we can notice that indeed it is not producing a single vortex, tip vortex, but rather two distinct weaker vortices. And that's pretty great, but that's theory, and it's even better to put it to practice. And the great thing about working with Craig is that he can actually build propellers, and he can build them pretty fast. So here's one blade you see to the left, and it was actually applied very recently to the Sling Whisper you see on the right. And notice the non-planar tip on the right. So the Sling Pilot Academy actually made quite a nice YouTube video about this. It's about 20 minutes long, and you can find that on YouTube. And I just want to show you some of the highlights of that video. Now, I'm not even sure if the sound's going to work, but it's obviously not going to be great, so we have to go with their testimony. And they're actually saying it's more like a fan than a propeller during the static test. And once it was up in the air, they were discussing that they couldn't really hear it because the noise level was being dominated by other aircraft way further out. So far, it's been a success. And if you are interested in seeing this prop, the airplane I just showed you is actually here, and they have a booth here. So you can go over there and pay them a visit. And I want to end with one more video that I want to share with you, and it's really there to bring home the point that all the topics that we discussed today, from aerodynamic lift to induced drag to parasitic drag and even propeller performance, are in reality always interacting. They are never going to be separate topics, and for an actual airplane performance, sometimes the interaction is going to be more important than the topic by itself. And that brings me to the end of my talk. I really hope you learned something today. You can contact me at info@mvaero.nl, and I thank all of you very much for coming and listening.